Hello. Today we're going to look at another kind of research design, quasi-research design. And we saw that we used Campbell and Stanley's classical typology of research designs. We looked at experiments. Now we're going to look at things called quasi-experiments, another kind of research design. And it's quasar because I know you had many years of Latin like me. Quasar means almost or like. So a quasi-experiment is like an experiment, but it's not up to the same highest level that experiments are. Because the difference is that in experiments, you can, through randomization, form the experimental and the control group. And randomization sets them equivalent. And it's good when you start with that confidence that the groups were equivalent. Then when you give the experimental treatment to the experimental group, any changes you see different in the experimental group than in the control group is due to the experimental treatment. Here in the quasi-experiment, you are not able to randomize and form groups in this way. And there's many situations in which you can't do it. Say there's a new program introduced in a high school, and you want to test how it's doing. Well, if you wanted to use an experiment, you would randomize the students into two groups. The experimental group would get the new program. The other people would not. But there would be a problem because the parents in the schools would object to people being randomly placed in a control group and not getting this new program that's supposed to be so good. So we have quasi-experiments to make up for that. In a quasi-experiment, we have groups, we have experimental treatments, but we don't have randomization, so it's not as strong. There's different kinds of quasi-experiments, and I'm going to look at a number of different kinds, starting with a design called the contrasted group design. And here's what a contrasted group design looks like. Notice my props. They're real professional, aren't they? In a contrasted group design, what you have is, just like an experiment, you have these two groups. This is going to be the experimental group, and this is the comparison group. We don't call it a control group because control group, it means to imply that you form the groups through randomization. These groups were not formed from randomization. And here I'm using as an example Eleanor Roosevelt High School, right here in PG County, outside of Washington. If they got a new government grant to set up a new drug education program for 10th graders, you might want to test, does it work or not, right? And so here we have, in a contrasted group design, we have the 10th graders from Eleanor Roosevelt High School, and we need another comparison group to compare them to. Couldn't form them through randomization, but they're naturally occurring. I have here the 10th grade at Greenbelt High School, a high school down the road. It's very similar to Eleanor Roosevelt, and it would be a good comparison group. So what you have to do is you have to get permission from the administration of Greenbelt High School for their 10th graders to participate in this study. And so what you do is you do a pretest, try to figure out what do kids know about drugs, their tendency to take drugs. These are the sorts of things you'll get in the pretest. You'll get it for Eleanor Roosevelt High School, and then you'll get it for Greenbelt High School. Then the X means experimental treatment given to the kids in Eleanor Roosevelt High School. They're going to get the drug education program. Probably go on for a semester or 2 semesters. Then finally you get a post-test for both the Eleanor Roosevelt High School 10th graders and the Greenbelt High School 10th graders. And what you want to know is changes going from here to here. Let's compare them to the changes here to here. And if there are bigger changes or different changes at Eleanor Roosevelt High School, then you think it's due to the fact that they have this drug education program. And so the Greenbelt High School 10th graders served as a comparison, so you could compare them. Imagine if you didn't have this bottom group at all like this, and you had Eleanor Roosevelt High School. You gave them a pretest, they got the new program, and then you gave them a post-test. Well, you might see changes between the pretest and the post-test, but you're really opened up to this objection that how do you know this change from the pretest to the post-test took place because of the drug education program? That's why you need this comparison group. So that's how this contrasted group design works, quasi-experiment. Now, there's another group of quasi-experiments called the extended time series. And the rationale in an extended time series is to take snapshots through time of groups or sometimes the same subjects, sometimes different subjects, and to make inferences as to what's going on in these groups over time. Now, there's two kinds of extended time series experiments. The first one is a special one. It's called a panel. The second kind of extended time series quasi-experiments would be a regular time series design. Now, what's the difference between a panel and a time series design? Well, in a panel, what you do is you use the same people and you study these same people over time. You make observations of them and you see how they change over time. Classical panel in political science was done by Professor Lazarsfeld, where he studied people, I think it was Erie, Pennsylvania, during an election year. And they interviewed people, they found out their attitudes about politics, they found out what they thought about the election, and they did that in an election year, January, February, March, April. And they could see the changes in people's attitudes over time, changes that might come with the convention or other events that take place during a campaign. That's the general structure to a panel. You have the same people. Now, another famous panel is the Framingham Heart Study. Anybody from Massachusetts? Well, Framingham, the city of Massachusetts, was started decades ago in a study as to why do people have heart disease? Some people have it and some don't. So they studied it, thousands of people in Framingham years ago, and they looked at their lives, their lifestyle, their condition of their heart, and they studied them over many years, over decades. And out of that, they got an idea as to what are the risk factors for coronary heart disease. This is what you do when you do this time series like that. These are panels, and panels have a difficulty. First of all, it's hard to find people willing to participate in panels. You got to come back, you got to do it all the time. Not everybody's willing to do that. Another problem is people say, yeah, I'll be in it, and they're in it at the beginning and they drop out. So dropping out is a problem. You got to encourage people to stay in your panel. And then also there's this effect that participation in a panel tends to freeze the effects of the participant. It has this effect of freezing them. So they gave a certain answer in January. They tend to give that same answer in February because we don't want to really be inconsistent over time. So that's a problem. Now let's talk about another, not strictly an academic kind of time series, but this is an interesting one that was carried out in cinema. Anybody ever see the 7 Up series of films? Well, this is a series of films. What they did, Michael Apted is the maker of the 7 Up series. In 1964, in Britain, he chose 14 children, some male, some female, different races, different social classes. So you have these 14 children, they're 7 years old in 1964. They put the camera down and they interview each of them individually and what they're like, all 14 kids. Put the camera away, they wait 7 years. When they're 14, sit down and they interview them again. Different questions because they're in a different stage of life. And you get a feeling for how the kids are changing. Then they did it at 21, 28, every 7 years, all the way up to, I see in 2019, they did the 63 and up. So it's called 7 Up, 14 Up. 63 Up is the last one. I haven't seen it yet, but I'm eager to because well, you could binge on this if you get a hold of it, and you could watch these people grow up over time. This is that rationale behind a time series, and it's really effective. Now that's the panel, looking at the same people over time. Now the regular time series takes snapshots over time, but it's not necessarily of the same people. Uh, Elections do this all the time. Anybody ever hear tracking polls? Well, you have an election going on. You might be interested in what's going on between Trump and Biden in, say, Ohio, the state that I grew up in. Tracking polls will take polls over time and see how is the poll changing over time? How are people changing over time? So as you get closer to the election, an effective way to do a tracking poll would be on the telephone. randomly call 400 Ohioans in on Monday. Then on Tuesday, 400 more. On Wednesday, 400. Now bring them all together, you got 1,200. 1,200 is a good number for a political poll. You get a margin of error about 3.5 percentage points, right? So you got Monday, Tuesday, Wednesday, 400 each night. Then Thursday, you do 400 more and you drop off the 400 from Monday. Now you take those 1,200. And over time, you can interview 400 people at a shot. And the older interviews, you drop out and you can watch people change over time during an election. Uh, that's one way to do a time series, one use of it. The classical time series design was done in the state of Connecticut in the 50s. And here's what Connecticut was interested in. They had a high level of traffic fatalities, and they thought, wow, if we could slow down people, it would be good, and we could cut the fatality rate. How do you slow down people? Well, I can tell you, you give them tickets for speeding. But you pull somebody over, I wasn't going 50. How do you know I was going 50? You need a way of measuring that. And the Connecticut State Police came up with the idea in the 50s. They have this new technology from World War II, radar. Radar was designed, it was designed to watch for submarines, to watch for planes coming in. But one thing they can do with radar is they can tell how fast an object is moving that's been hit with the radar beam. And so in Connecticut, what they thought is, why don't we use radar to enforce the speeding laws, give out tickets, and we can thereby, we think we can cut the fatality rate here in Connecticut. So what happened is the year before the program, it's 1955, before the program was implemented, they had 324 fatalities on Connecticut roads. They put this radar program into effect. They started giving out tickets. Then you're waiting for 1956 to see does the fatality rate move up or down? And the fatality rate moved from 324 down to 284 after they initiated this program. Now you can just see the announcement. Everybody's eager to see how it's doing, and they announced that we dropped the fatality rate by 15% because of this radar program we put into effect. Now that's pretty typical of how we act. We think, well, a party in power might cut taxes, and then look at how the economy's doing. It's doing that way because we cut taxes. Well, not so fast. There's a problem with that. Just because you do something and then you look at what follows after it doesn't mean the thing that you did actually caused it. That's a logical fallacy. We got a fancy Latin name for it. Post hoc ergo propter hoc. After this, therefore because of this. That's considered a fallacy. Just because something comes after something else does not mean it was caused by that original thing. So you got that problem here in Connecticut. The fatality rate went down when you put the radar program into effect, but you don't know if it's because of the radar. So how do you deal with that? You think it's because of the radar program, but there are people that would say, wait a minute, it might be due to some other factor. I might just be the person doing that. Being a member of the Porsche Club of America, I'm not crazy about radar. So there are people who will snipe at this and say, wait a minute, how do you know the radar knocked the fatality rates down? Think in your mind. There could be other explanations, couldn't there? What could cause the rate of fatalities to go down between 55 and 56? It has nothing to do with radar. Well, the weather could be different, right? I mean, more severe weather one year, more accidents. You could have more fatalities. Another thing, cars could be becoming safer. Safety in automobiles is a big deal. If cars become safer, then you would expect the fatalities to move down, having nothing to do with radar. That would be the idea. Another argument would be that, well, maybe the fatality rate went down because it had been coming down for years and years, and this was a natural part of this progression down. That's one. Also, safety in roads. If the roads become safer, and believe me, the roads are safer now than when I was a little kid. If the roads are made safer, then that could account for why the fatality rate went down. So this is what the researchers were confronted with. And so what they did is they said, well, let's gather information on the fatality rate in Connecticut going back to like 1951, 51, 52, 53, 54, then 55. Then the radar program comes in. They get 57, 58, 59. They gathered that, and then they said, we have to have a comparison to compare Connecticut to. And they came up with the idea, why don't we take as our comparison states the states that ring Connecticut, the states that are around it, and let's get their fatality rates from 51 up to 59, and let's compare them to what happened in Connecticut. And here I have the results of their getting the fatality rates for all those years. You can see this line here. This is where the radar was put into effect. And then you see Connecticut is that solid line. So you can see the fatality rate in 51 was up there just about 12, dropped down to about 10, back to 12. Then it went back down. Then it went up. This was that year they were concerned about, up to a 13. That's where they had the 324 fatalities. Then they put the line, the radar into effect, and then they've got it for 56, 57, 58, 59. So you can see Connecticut is moving like this, moving down. Once you get this time series, you can immediately remove some of the doubts you had about radar causing the dip in fatalities. For instance, you can do away with the hypothesis that, well, the number of fatalities were going down over time and they naturally went down when you put the radar program into effect. They weren't naturally moving down. Then you get to the dotted lines. These are the comparison states, the states that bring Connecticut. And now we want to look and compare Connecticut to the comparison states. And we can see the comparison states are a little higher than Connecticut. Then Connecticut had moved up. Then look at how Connecticut moves down. But the comparison states did not move down nearly as much. And the comparison states did not have radar programs. So now that you have this data from the comparison states, think in your minds all of the alternative explanations as to why Connecticut's having this dip in their fatality rates. You can rule out weather, don't you think? I mean, do you really think Connecticut has very different winters from the comparison states surrounding it? That clouds just sit over Connecticut and not elsewhere? That doesn't seem believable, does it? Or safety in cars. It's not safety in cars which led to this. The comparison states are getting the same cars. Now, here we weren't buying Japanese cars then. We have almost all American cars. But I can tell you that, in fact, when they come off the assembly line, they aren't going, well, that's an unsafe one. We'll send that one to Connecticut. Connecticut's getting the same cars as the comparison states. And, well, we could gather further information on safety of the highways. And you could find out that though this is going down for Connecticut, the fatality rates, the roads aren't being made any safer in the 50s, and the cars really aren't being made safer in the 50s. That would come later, in which the safety of the road would really become important. So that now on a road, when you hit a utility pole, it's purposely made that it snaps off and doesn't put your engine on your lap. It wasn't like that at this period of the 50s. So you can gather that information, rule that out, and this is how this quasi-experiment works. You have a comparison group, and you compare the experimental group that you're looking at that got the radar program Connecticut, and make your inferences. Now, there's a final quasi-experiment that I want to tell you about. And this quasi-experiment was concerned with winterization of houses and how can we conserve fuel in the United States. We're concerned about that now. We want to have a smaller carbon footprint, and what we want is we want to heat our houses, but we don't want the heat to escape easily, so we have to use a lot of fuels to do it. In Seattle City Light, the utility conducted a quasi-experiment in which they tested whether or not winterization for people that are poor, whether winterization of their houses would lead to a savings in energy that was worth all the money you put into the winterization. And so what they did is they had a program. You had to be below a certain financial level. If you came, they announced it on the radio and in the newspapers, and if you qualified, you came forward, they would inspect your house, and they would put in insulation in the attic, caulk windows and caulk doors. There was a whole winterization program that people got. And then they're interested in this. Did this save much? Does it save much energy? Is it worth it? That's what they did, right? So people came forward and they were in the program, and the researchers had to evaluate this. Is it effective or not? First thing that comes to mind is do an experiment. As people come forward, you could randomize them into an experimental and control group, right? The researchers were of the opinion that it wasn't fair to the people who came forward, who wanted the winterization, that a coin flip meant they had to be in a control group and they wouldn't get the winterization. So they ruled out an experimental research design. Think in your mind, what else can we do? We need a comparison group. Well, you could get on the computer the families that had their houses winterized. Let's look at before the winterization, what their bills were in that year, and then look after winterization and see the change. How about that one? Well, you can't really do that. You don't know if there are other alternative explanations. The winter could be different. The wind is different. Uh, the way the family lives in the house could be different. There are other explanations. That would be a pre-experiment. That is not a very good one. So here's the design they came up with. People came forward in year one. They met the qualifications. Their house were winterized. They got their house winterized, right? And then they waited to year two. And the second group of people, they came forward, they met the criterion, they were below the poverty level, and they were winterized. So now you use these people who came forward in the second year, you use them as a comparison group. And this is how we can kind of diagram how this quasi-experiment went. I got to do it this way so you could read it, right? This is year one, and group one comes through. They're winterized, and then we get year two, and we look at year one and year two. Did the winterization make a difference in their bill? And then we wait till the next year, and another group of people come forward that meet the same criterion. This is your comparison group. They're winterized. And then what we do is we look at group one. How did their bill change from year one and year two? And we take group two. How did their bill change from year one and year two? And you compare them. You subtract the year two from the year one for group one, and you subtract the year two, you subtract the year one from the year two from group two, and you compare these two. What is the drop like? And if the winterized group that came forward the first time, if their bill dropped more than the other people in two, then you think that drop is due to winterization. Uh, the conclusion the researchers came to was, in fact, their bills would be cheaper, and that over a period of 30 years, they would save $485 in their utility bill. Now, I mean, you give that information to people, they decide, should we make this program permanent? And it's not easy to make that determination. I mean, 30 years is a long period of time. There's a lot of inferences, estimates, and what the bills are going to be like in 30 years. So there's a lot of air there. But all in all, this gives decision makers a better look at in a rational way. Does this program work or not? Do we really save money by doing this program? And that's what I'm going to tell you about quasi-experiments. Now, what we'll do next time is we'll move on in research design, and we'll look at correlational research designs, which are important research designs now. What I'm going to try to do is on Blackboard under our class, I'm going to set up a discussion board where you can enter your comments into quasi-experiments and what we've been doing here. So go to Blackboard and take a look. Thank you.